The ground feels still, but it isn't. The whole galaxy is moving. It's going over 1.3 million miles per hour. Something is pulling it, a gravitational anomaly. We can't see it. There's a structure out there, a colossal one, in the darkness. Its pull might even come from beyond our universe. Your home is adrift. It's in a current, heading toward a destination we don't know. The story of our motion doesn't start with a telescope. It starts with a hum. A quiet hum from the very beginning of time. In the 1970s, astronomers were looking at the cosmic microwave background. That's the oldest light we can see. It's radiation that fills the whole universe. It's a fossil, from when everything was hot and dense, and now it's stretched out and cold. They wanted to map its temperature. They expected it to be smooth. The same in every direction, but it wasn't. They found an asymmetry. One part of the sky was a little warmer, a hot spot, and the part directly opposite was a little cooler. A cold spot. That pattern has a name, the dipole anisotropy, and it was evidence, the first real evidence we aren't at rest. The whole solar system was moving through that ancient radiation. It created a Doppler effect. We were heading toward the warm spot, away from the cold one, and we were moving fast, over 200 miles per second. That was the first direct measurement, our motion through the cosmic framework. Later, in the early 90s, a satellite called COBE confirmed it, the Cosmic Background Explorer. It painted a clear picture, but solving that mystery created a bigger one. Because this motion they measured, it wasn't just the Sun orbiting the galaxy. It was the whole Milky Way galaxy, moving, caught in a vast current. Our local journey was just a small eddy in a galactic river, flowing toward an unknown sea. That subtle temperature difference in the ancient light, that was our first glimpse of the current. The first clue that something with unimaginable mass was out there, pulling not just on stars but on the fabric of our entire galactic neighborhood. That hum from the beginning gave us a speed but not a direction. We knew we were moving. To find the source, you had to separate two motions happening at once. The first is the expansion of the universe itself, space stretching, carrying galaxies apart. The farther a galaxy is, the faster it seems to move away. That's the bedrock motion. But layered on top of that is gravity's specific tug. A galaxy caught in a cluster's pull, or part of a stream heading somewhere. That second motion is called peculiar velocity. It's the deviation from the pure expansion. Think of a leaf on a wide river. The river's current carrying everything downstream, that's the expansion. But the leaf might spin or get caught in an eddy or drift toward a rock. Those specific movements are its peculiar velocity, caused by local features. In the universe, those are the gravitational wells of superclusters, the empty voids. To find our drift, scientists measured the redshift for thousands of galaxies. How fast they're moving away. Then they subtracted the velocity expected from pure expansion based on distance. What was left was the peculiar velocity. The true drift. A galaxy's own story written in gravity. This work is done through peculiar velocity surveys, projects like 2MASS, the Cosmicflows project. Decades collecting this data, charting motions across hundreds of millions of light years. A dynamic, three-dimensional map of our neighborhood in motion. And when you plot all those residual velocities, all those peculiar motions, a pattern emerges. They are not random. Across an immense volume, galaxies are streaming. A coherent bulk flow. A vast river within the river, all trending the same direction. Our Milky Way is not alone. We are one leaf among countless others, caught in the same immense current. This map, from the fingerprints of gravity on light, doesn't just show we are moving. It shows where we are going. A collective arrow drawn by millions of galaxies, pointing toward the source of the pull. The map was complete. The destination was clear, but what was waiting at the end of that arrow? The map pointed toward Centaurus and Norma, a direction in the southern sky. But when you looked with optical telescopes, it was mostly a blank wall. Dusty, A thick, star-studded plain of our own galaxy was in the way, gas and dust and countless stars. It blinded the traditional view. Astronomers called it the Zone of Avoidance, a frustrating blank spot on the charts. The universe's secrets were hidden behind our own galactic clutter. In the 80s, a team of 7 astronomers, later called the Seven Samurai, they decided to work around the blindness. They couldn't see through the zone. So they mapped what they could see around it. They charted the motions of hundreds of galaxies nearby, tracing the lines of their gravitational flow. Like following a current in a dark river, and all those lines of motion converged, not on something visible, but on a point deep within that obscured zone. The math was undeniable. Something with staggering mass was there, pulling everything toward it. They named it the Great Attractor. The scale was difficult. This hidden structure had a mass thousands of times greater than our Milky Way. It wasn't a single object. It was likely a massive confluence of galaxies. A dense knot in the cosmic web. A galactic supercluster. Its gravity dominated our entire local neighborhood. It explained a significant part of our motion. But peering into its heart was still the challenge. To see through the zone, science needed new eyes. Eyes that could see the heat of stars through dust. Or the radio whispers of hydrogen gas. Infrared telescopes, like on the 2-micron all-sky survey, they detected the glow of stars piercing the fog. Radio telescopes mapped hydrogen, revealing the skeletons of hidden galaxies. Gradually, a shadowy picture emerged. The Great Attractor was real, a colossal gravitational landmark, the most significant one in our immediate cosmic vicinity. But this discovery didn't provide a final answer. It deepened the mystery, because when scientists accounted for the pull of this hidden monolith, the math still didn't balance. Our observed speed was still too high. The Great Attractor was pulling us, yes, but something even more powerful, something far beyond it, was pulling the Great Attractor itself. Our river was flowing toward a local waterfall, but the entire river system was tilting toward a distant ocean. Vast and unimaginable, the search wasn't over. It had found its first major clue, and in doing so, it pointed to a destination infinitely more strange. The Great Attractor was a landmark, but it wasn't the end. The math still didn't work. Even with its pull, our galaxy was moving too fast. The gravitational sum was wrong, something was missing, so the source couldn't be a single point. It had to be a structure, something on a scale we were only starting to see. The search had to zoom out, far beyond our local neighborhood, to see the true shape of the current. In 2014, a team led by R. Brent Tully published a new map of our cosmic vicinity. They weren't just plotting galaxies, they were charting their motions, tracing the flows of gravity. What emerged was a new definition of home. They gave it a name, Laniakea, from the Hawaiian, meaning immense heaven. Our supercluster, a vast web of over 100,000 galaxies, spanning 520 million light-years. In this immense heaven, the Great Attractor isn't the end, it's the center, the dominant gravitational valley of the whole structure. To understand Laniakea, think of a continent. A landmass like North America, with its mountains and river basins. Now imagine that continent is made of galaxies. The Great Attractor is like the lowest valley on that continent, the basin where a great river gathers its waters. Every stream on that continent, if left to flow, finds its way to that central basin. Laniakea is that continental watershed for gravity. Every galaxy within it, including ours, is part of that flow, streaming inward toward the gravitational heart. Our motion isn't a lonely voyage. It's a supercluster scale in FAL. We are one tributary in a cosmic river system, all converging on the same point. This reframing was profound. It showed our place in a structure of breathtaking scale. But it also underscored a deeper mystery. When they calculated the pull of the entire Laniakea supercluster, all 100,000 galaxies flowing together, it still couldn't account for our galaxy's full speed. The numbers were off by a significant margin, so the river system itself was tilting. The entire continent of Laniakea, this immense heaven, was itself in motion. Being pulled by something even greater, lying far beyond its borders, the source of the anomaly receded again, into a darkness more profound than any zone of avoidance. It wasn't hidden behind dust. It was hidden beyond the edge of everything we called home. The river of Laniakea was tilting. That tilt had a name, dark flow. It was one of the most provocative ideas in modern cosmology. It came from looking at the emptiest places in the sky. The method was ingenious. Scientists studied galaxy clusters, but not by their light. They looked at their shadows on the cosmic microwave background. They used something called the kinematic Sunyaev-Zeldovich effect. The cosmic microwave background is that ancient, uniform light from the infant universe. When a massive galaxy cluster moves, the hot gas inside it scatters that ancient light. It leaves a faint imprint, a subtle distortion in the temperature. By measuring this distortion, astronomers could figure out more than just the cluster's location. They could tell how fast it was moving and in what direction. It was like reading the wake of a ship in a perfectly still sea. In 2008, a team analyzed data from hundreds of clusters. They expected to see random motions, little eddies and swirls as clusters tugged on each other locally. But that's not what they found. The clusters were streaming, all together, in a coherent bulk motion. And this stream was aligned. It pointed back toward the same general direction as the Great Attractor, the heart of Laniakea. That was strange enough. But the truly shocking part was the scale. This dark flow, as they called it, was detected in clusters billions of light years away. At such distances, the expansion of space should have washed out any local gravitational pull. The known mass of the entire observable universe, all the galaxies and dark matter we can account for, should not have been able to create a pull that coherent over that scale. It was as if every leaf on a continent-sized river was drifting the same way. But the river itself was tilting because of a mountain range on another continent, far beyond the horizon. The implication was staggering. If the dark flow was real, its source could not lie within our observable universe. The gravitational anomaly pulling us might originate from beyond the cosmic horizon, from a region of space-time whose light has not had time to reach us since the Big Bang. Or, in an even more mind-bending possibility, the pull could come from something entirely outside our universe. A pre-Big Bang structure, a scar in the fabric of reality from a time before time, or a gravitational tug from a neighboring universe in a vast multiverse, brushing against our own like sheets in the wind. This theory didn't just push the mystery to the edge of the map. It suggested the map was fundamentally incomplete. The idea ignited a firestorm. Critics argued fiercely that the signal was a systematic error, an artifact of how the data was processed, or an incomplete understanding of the cosmic microwave background itself. They pointed to later studies that failed to replicate the finding with the same strength. The debate was and remains a fierce one, fought in the pages of scientific journals and at conferences. It's a perfect example of science at its most contentious frontier. One side sees a fundamental flaw in our measurements. The other sees a fundamental flaw in our model of reality. The dark flow, whether a profound error or a profound truth, forces a humbling question. Are we being pulled not just by something we cannot see, but by something we, by definition, can never see? The search for the source had now ventured into the realm of pure geometry and theoretical physics, where the answers might lie in the shape of nothingness itself. The dark flow is a controversial idea. It's invisible, so to find something more tangible, you look back into the visible universe. You look toward a structure of staggering mass. It bends the paths of galaxies around it. That structure is the Shapley Supercluster. If the Great Attractor is a deep valley in Laniakea, then Shapley is a mountain range on a different continent. It's further out in the same general direction, about 650 million light-years away. And it's not just a collection of galaxies, it's a concentration of power. Shapley is a supercluster of superclusters, a dense knot. Dozens of rich galaxy clusters are packed together there by gravity. Each cluster holds thousands of galaxies. It's the single largest concentration of mass we know of in our local, observable universe. Its gravity creates a well in space-time. Everything nearby feels that well. Think of it as a cosmic sumo wrestler, standing on the far side of the Great Attractor. The attractor pulls us toward the center of our own supercluster. But Shapley, though much farther away, is so immensely heavy. Its gravitational reach extends across the void. It tugs on the Great Attractor itself. It tugs on every galaxy in the stream, so there's a complex gravitational tug-of-war. Our Milky Way is caught in the middle. We feel the strong, nearby pull of the Great Attractor, drawing us into Laniekea's heart. But we also feel the distant heft of Shapley, pulling the entire system further on. Some models suggest Shapley's influence might be the dominant one. That its overwhelming mass is the primary engine behind the bulk flow of galaxies in our region. In that view, the Great Attractor isn't the final destination. It's a waypoint, a local feature in a much larger current, a current flowing toward Shapley's immense gravity. This introduces a concept, the cosmic sum of forces. Our motion isn't dictated by a single mystery object. It's the net result of every massive structure pulling on us. It's a vector sum, an arrow drawn by the combined gravity of the Virgo cluster, the Great Attractor, the entire Laniakea supercluster, and the colossal Shapley supercluster. Plus countless other filaments and voids. We are navigating a landscape of titans. Each one exerts its influence. Our path is the delicate balance of them all. Right now, the mathematics suggest something. Shapley's pull, combined with the attractors, might finally account for most of our observed velocity. It offers a solution within the known universe, without needing dark flow. Yet, even with Shapley in the equation, some subtleties in the measurements remain. The numbers get very close, but the fit isn't always perfect. That leaves a sliver of doubt. A space for the unknown. Is the Shapley supercluster the final answer? The master conductor of our local stream? Or is it just another piece in a puzzle that extends even further, toward something we have yet to name? That sliver of doubt points to something fundamental. The universe isn't just a collection of isolated giants. It's a web, a vast, interconnected architecture, matter and emptiness. To understand the forces moving our galaxy, you have to see this whole cosmic web. Picture it not as a starry void, but as a colossal sponge. The solid parts of the sponge are the filaments, long, thread-like chains of galaxies, millions of light years long. They weave and intersect. They form a labyrinth. At the intersections of these filaments, you find the densest knots, the superclusters Laniakea, Shapley. These are the nodes of the web. And between the filaments, you find the voids, immense, nearly empty regions. They can span hundreds of millions of light years. This is the large-scale structure of everything. A cosmic web spun by gravity over 13.8 billion years. This structure didn't appear by accident. In the early universe, there were tiny quantum fluctuations, imprinted on the primordial soup, slightly denser patches of matter. Over eons, gravity acted on those seeds. It pulled matter from the emptier regions toward the denser ones. Matter flowed along the emerging lines of force, like water finding the paths of least resistance down a hillside. This process sculpted the voids. It built up the filaments. The filaments became the highways of the cosmos, the primary channels. Along these, galaxies and galaxy clusters stream, drawn by the deeper gravitational wells at the nodes. So our motion isn't a lonely arrow shot toward a single dark mystery. It's a journey along one of these grand cosmic highways. We are within a filament, part of a river of galaxies, flowing toward a more massive intersection in the web. The Great Attractor and the Shapley Supercluster aren't just isolated hills. They are major junctions, powerful gravitational anchors where multiple filaments converge. Think of it as navigating a vast, bumpy landscape. But this landscape exists in 3 dimensions. The superclusters are the mountain ranges. The voids are the deep oceanic trenches. Our galaxy is like a ball rolling on this terrain. Its path is dictated by the entire topography. It rolls toward the nearest low point, but that low point is itself sliding down a slope toward a deeper valley. A local hill might deflect it slightly. A distant mountain range exerts a steady, gentle pull on the entire region. Our trajectory is the sum of all these features. The pull of the Great Attractor is the steep slope right beside us. The heft of Shapley is a massive mountain on the horizon, tilting the whole continent, but also the emptiness of the neighboring void, a place called the Dipole Repeller. It might be pushing us as much as the dense knots are pulling, because in gravity's geometry, an absence of mass is as influential as a presence. An empty void creates a kind of gravitational hill we roll away from. This web-like perspective changes the question. We aren't searching for a single hidden monster in the dark. We are mapping the currents of a cosmic watershed. Every filament, every node, every void contributes to the flow. The anomaly isn't necessarily one thing. It is the integrated gravity of the entire visible universe. As structured by this intricate web, our speed and direction are a reading of that total gravitational field. So when measurements don't perfectly match our models of the web's mass, it suggests one of two things. Either our map of the web is still incomplete. There are more filaments, more massive nodes hidden behind zones of avoidance, or our understanding of gravity itself on these immense scales needs refinement. The web is both the map and the mystery. Its grand design holds the answer to our journey, and perhaps to the very nature of the force that sculpted it. The cosmic web is made of something we can't see. Its filaments, its nodes, the structure that dictates our motion. It's not sculpted by the galaxies alone. There's an unseen architect. To understand the true scale of the force pulling our galaxy, you have to meet the universe's dominant component, dark matter. And this isn't a rare substance. For every particle of visible matter, every star, every planet, every speck of dust, there's about 5 times more dark matter. It doesn't emit light. It doesn't absorb or reflect it. It's invisible across the entire spectrum. We can't see it, but we can feel its gravity profoundly. Think of a massive structure, the Great Attractor, the Shapley Supercluster. The galaxies you see there, those brilliant cities of stars, they're just the streetlights. They mark the location of something far larger and darker. The true mass of these cosmic landmarks isn't in the lights. It's in the vast, invisible halos of dark matter that envelop them. Each galaxy, each cluster, sits at the heart of a colossal sphere of this mysterious material. A gravitational well carved into space-time by pure, unseen mass. These halos extend for millions of light years beyond the last visible star. They are the scaffolding, the hidden framework the visible universe is draped on. This changes everything about the pull we feel. When we say the Shapley Supercluster is pulling us, we're not talking primarily about the gravitational tug of its thousands of galaxies. We're talking about the combined, deep well created by their immense, overlapping dark matter halos. The visible galaxies are just tracers, bright buoys floating on the surface of a dark, massive ocean. Our galaxy's motion is a current within that ocean. We're responding to the contours of an invisible landscape. So the anomaly pulling us is a map of dark matter. Our speed and direction are a direct measurement of how this unseen mass is distributed across vast volumes of space. This is how scientists use our motion and the motions of thousands of other galaxies as a probe. By tracking how galaxies stream and flow, they can reverse engineer the distribution of the mass causing that flow. They are charting the unseen. It's a form of cosmic echolocation. We send out no sound, but we listen to the motions of the stars, and from their drift we infer the shape of the darkness. Every peculiar velocity measured, every bulk flow mapped, adds another day to point to a 3-dimensional chart of dark matter. The Great Attractor isn't just a cluster of galaxies. It's a peak in the dark matter density of our local universe. The Shapley Supercluster is a mountain range in that same hidden topography. So the search for what's pulling us has always been, at its core, a search for dark matter. We're not being pulled by a single hidden monster. We're being carried by the cumulative gravity of an invisible architecture. An architecture that forms the backbone of every filament, every void, every node in the cosmic web. Our journey is a voyage through a sea of shadow. And the current we feel is the deepest, most fundamental current of all. It's the flow of gravity itself, tracing the contours of the universe's true, hidden face. This realization doesn't solve the mystery, it redefines it. The question is no longer just what is out there. It's what is dark matter, and how does its silent geometry guide the fate of everything we see? Our map of the cosmic web has this permanent blind spot. The zone of avoidance. It's a fundamental gap. A whole area of sky where our view is blocked by our own galaxy's disk, the stars, the gas, the dust. For a long time, that area was just blank. And it's right in the direction we're being pulled. The heart of the Great Attractor was sitting inside it. So to solve that, we had to learn to see through that wall, which meant we needed new eyes, not eyes for light, but instruments that could sense what light can't get through. Radio telescopes became the first key. Neutral hydrogen gas, the raw material for stars, it fills spiral galaxies, and it gives off this faint radio whisper, a specific frequency. So they tuned big dishes like the Parkes telescope in Australia to listen for that hum across the zone of avoidance, and they started mapping the skeletons of hidden galaxies. They weren't seeing starlight. They were tracing the cold hydrogen that outlined entire galactic structures, all hiding behind the Milky Way's glow. That survey, the HI survey, it painted the first ghostly pictures of what was in the dark. It showed dozens, then hundreds of galaxies we never knew were there, all adding their mass to the pull we feel. At the same time, from above the atmosphere, space telescopes gave another view. Infrared light has a longer wavelength. It can slip between dust grains that block ordinary starlight. Observatories like WISE and Spitzer, they scanned the zone in infrared. They detected the collective warmth of billions of hidden stars. Their glow shifted into that longer, penetrative wavelength. It was like using thermal imaging to find the heat of cities hidden in a fog. These two approaches, radio mapping and infrared sensing, they started lifting the veil. And what they found was staggering. In 2016, a team announced the discovery of the Vela Supercluster, a colossal structure of galaxies, completely hidden behind the Milky Way's plane. It's enormous, rivaling the size and mass of the Shapley Supercluster itself. And it's much closer to us, right in the flow toward the Great Attractor. Its gravitational pull, missing from all our calculations before, is profound. This wasn't a small missing piece. It was an entire section of the puzzle, hidden in plain sight. The ongoing work in the zone of avoidance, it's more than filling blanks on a map. It's a direct hunt for missing mass. Every new galaxy cluster found, every filament traced through that once impenetrable region, it adds to the gravitational sum pulling on us. It's entirely possible that the final explanation for our motion, that last bit of velocity theories, can't account for lies in a concentration of mass we haven't catalogued yet. Still hidden in that dusty zone, completing this map is the ultimate test. If, when the last blind spot is lit up, the gravitational ledger finally balances, then the anomaly is solved. The pull explained by the combined might of the attractor, Shapley, Vela, all the other visible and dark structures in the cosmic web. But if the map is finished and the numbers still don't add up, then the mystery deepens. In a far more radical way, the search would turn from the unseen mass in the darkness to the very laws that govern how mass and gravity shape our reality. The hidden architecture of dark matter is a map we read indirectly. To test that reading, we build entire universes, not real ones, but inside supercomputers. These are cosmological simulations, vast digital labs where you can rewind time, set the initial conditions of the cosmos, and let physics play out over billions of virtual years. It's how we model the cosmic tug of war in silicon, Projects like the Millennium Simulation, Illustris TNG, they start with a virtual box of space, filled with a simulated soup of dark matter particles and ordinary gas. You program in the known rules, the initial quantum fluctuations from the Big Bang, the relentless pull of gravity, the complex behavior of gas as it cools, forms stars, explodes in supernova. Then you hit start. The supercomputer calculates gravitational interactions between trillions of particles. Over eons of simulated time, the virtual universe evolves. Filaments of dark matter emerge, galaxies form at their intersections, voids grow vast and empty. The cosmic web weaves itself from pure math and physics. The result is a breathtakingly realistic virtual cosmos, a time-lapse movie of the universe's entire history. Scientists can explore this digital universe like our own. They can pick a virtual galaxy that looks like the Milky Way and track its motion. They can measure the bulk flow of thousands of virtual galaxies around it. See if a Great Attractor or a Shapley-like supercluster forms in the simulation. And most importantly, compare the strength and coherence of these simulated flows to the one we actually observe. This is the ultimate test for our standard model of cosmology, lambda-cdm. That model is built on dark energy, lambda, and cold dark matter, the CDM. The simulations are built entirely on this framework. So when we run them, we're asking a direct question. Can the known ingredients and laws, starting from the observed early universe, produce a cosmic neighborhood that looks and moves exactly like ours? If the virtual Milky Way in the simulation ends up streaming with the same speed and direction as our real one, then the model is validated. The pull we feel is just the expected outcome of the cosmic web's growth. The combined gravity of all the simulated Laniakeas and Shapleys would be sufficient. The answers from these digital universes are profound but mixed. They show that large-scale bulk flows are a natural feature. The simulations do produce them. Virtual galaxies do stream toward massive attractors. This tells us our basic picture is sound. The gravitational tug-of-war between visible superclusters and dark matter halos can indeed create the kind of motion we're part of. Researchers can even use the simulations to weigh the contributions. They can virtually turn off the pull from a Shapley-like node and see how much the flow slows down. This helps quantify how much of our motion is due to which known structure. Yet, some analyses suggest a subtle tension. A few studies indicate the very largest, most coherent flows seen in our real universe, flows spanning over 1 billion light-years, might be slightly more extreme than what the standard model simulations typically produce. The virtual flows are there, but they might not be quite as strong or as aligned on the very largest scales as the one we seem to be in. This doesn't break the model, but it leaves a window open. It's the hint in the data that keeps the more exotic ideas, like the controversial dark flow from beyond the horizon, from being completely dismissed. These simulations are more than fancy video games. They are the testing ground for our understanding of reality. They let us run experiments on the universe itself, experiments we could never perform in the real world. When we compare our place in the cosmos to our place in the simulation, we are holding a mirror up to nature. And in the reflection, we look for discrepancies. For now, the reflection matches remarkably well, but the search for that one tiny, telling flaw, the clue that our map is still missing a continent, continues. In the glow of 1 million processor cores, calculating the fate of imaginary galaxies, the reflection in the simulation rests on a cornerstone, the law of universal gravitation. But if that cornerstone is flawed, what if the pull we see isn't a map of hidden mass, but a sign that gravity itself works differently, on the largest scales? That question leads to the most radical alternative, a theory that tries to erase dark matter entirely. Modified Newtonian dynamics, MOND. The idea is simple and disruptive. Instead of inventing an invisible substance to explain fast galaxy rotation, MOND says we adjust the math of gravity. It suggests Newton's law changes when accelerations become incredibly tiny. the kind you find in the sparse outskirts of galaxies, or in the drift between galaxy clusters. In that regime, gravity becomes slightly stronger than Newton or Einstein would predict. This extra gravitational kick, according to MOND, is what makes stars on a galaxy's edge orbit so fast. It's what holds galaxy clusters together, without dark matter glue. The motion is evidence for a modified force. So, could MOND explain the Great Galactic Current, the bulk flow toward the Great Attractor and Shapley? Could it be a product of revised gravity, not the pull of immense dark matter halos? Proponents argue it might. Under MOND rules, the distribution of the visible galaxies we can see might be enough to generate the large-scale flows. The coherent motion across hundreds of millions of light-years could be a natural outcome of how gravity links visible matter in this modified framework. There's even a relativistic version, TVS. It tries to fit modified gravity into a framework compatible with Einstein's general relativity, to explain things like gravitational lensing. This presents a fork in the road. One path says the universe is mostly invisible matter, but gravity is as we know it. The other path says the universe is only what we see, but gravity is the mystery. It's a fundamental clash. Mainstream cosmology has stayed on the first path. The evidence for dark matter is overwhelming. The way galaxy clusters bend light, gravitational lensing, shows mass distributions that match dark matter models. Not just the visible galaxies, the detailed patterns in the cosmic microwave background, that ancient hum. They are fit by a universe containing about 5 times more dark matter than ordinary matter. Computer simulations of cosmic web formation with dark matter. They produce a universe that looks uncannily like our own. For most cosmologists, these pieces form a consistent picture. One that MOND, in its current forms, struggles to replicate fully. Yet the persistence of MOND isn't stubbornness. It's science at its most vital. Cosmic anomalies like galactic rotation details or the largest bulk flows serve as the ultimate stress tests. They are places where our models might crack, revealing something deeper. The debate isn't just technical. It's a reminder that the force we think we know, the one that holds our world together, is still being interrogated by the cosmos. The great pull we feel is more than a destination. It's a question written in the motion of stars. A question that asks about the true nature of the force that guides them. Our destination is written in the gravity we're mapping now. The Milky Way isn't moving in a straight line. It's on a spiraling path, a kind of dance with a predictable end. First, there's a local merger. In about 4.5 billion years, our galaxy and Andromeda will start to collide. They're the two largest in our local group, and gravity has already locked them together. It won't be a crash of stars. Space is too big, stars too small. It'll be a slow gravitational tango lasting billions of years. The two spirals will pass through each other, their structures stretched and torn by tidal forces. They'll swing apart, then fall back together. After several passes, they'll finally merge. The result will be one giant elliptical galaxy. Astronomers have a name for it, Milkomeda. That new galaxy, our future home, will be the capital of the merged local group. But its story doesn't end there, because Milkomeda will still be caught in the same vast current that moves us now. Its path will continue, carrying it along the filament of the cosmic web, deeper into the gravitational basin of the Laniakea Supercluster. Over tens of billions of years, Milkomeda will stream toward the core of Laniakea, toward the region dominated by the Great Attractor. It'll join thousands of other galaxies in that central, dense hub. They'll all eventually merge, through that same slow-motion process, into one truly monstrous elliptical galaxy. A future titan sitting at the gravitational heart of our supercluster. That's the most likely local fate. To become part of a giant, red and dead galaxy at the center of Laniakea. But that future rests on an assumption that the larger-scale forces pulling Laniakea itself don't change things, and that's the great unknown. The immense gravity of the Shapley Supercluster is a constant, long-term tug. It's pulling the entire Laniakea structure toward itself. So as Milkomeda falls into Laniakea's core, Laniakea as a whole is falling toward Shapley. We're in a nested journey. A galaxy within a supercluster within a larger flow. That introduces a timescale question, which happens first. Does our local group fully merge and settle into Laniakea's heart before Laniakea itself is pulled toward Shapley? Or does the whole supercluster's motion distort the process? Current models suggest the local mergers happen faster. We'll likely become part of Laniakea's core long before the supercluster completes any major journey toward Shapley. But that core itself will be in motion, a massive island of stars being towed by a greater force. And then there's the most speculative layer, the controversial dark flow. If it's real, and its source is something beyond the observable horizon, then it represents a pull on a scale that dwarfs even Shapley. It would mean our entire local universe, Laniakea, Shapley. Everything we can see is itself adrift in a broader, invisible current. In that scenario, our ultimate destination isn't a place on any map we can make. It's a location in a cosmos we can't observe, governed by geometry or forces we don't yet understand. So our galactic future is a story of convergence, but also an endless journey. We'll merge locally, we'll gather into supercluster cores, but we may never reach a final, static rest. The universe is a dynamic web, and we're forever flowing along its strands, drawn by the invisible architecture of mass and the possible mysteries that lie beyond it. Our fate is to be part of something ever larger, in a cosmos that refuses to stand still. This idea has a real weight to it. It changes how we see ourselves in everything. For a long time, we thought we were at the center. The Earth was fixed, the stage. Then we found out it moves around a star, and that star was just one in a galaxy. And now we know even the galaxy isn't stationary. It's moving. It's a single part of something much larger. A gravitational pattern playing out over incredible distances. We're not at the center of that. We're carried by it. It makes you think about destiny, about chance. Are we just on a set path, flowing towards some fixed point? Or is it all chaos, the result of countless pulls and tugs, starting from how matter was scattered at the beginning? Science points to the second one. A beautiful accident of how things started and the laws that followed. But being in that current, it can feel like it means something. It changes how you look at it. From watching from the outside to being inside it. Every part of us, every star we see, is in that same slow drift. The forces that move galaxies are the same ones here. We're not separate. We're a way for the cosmos to be aware. It really puts our view in perspective. Everything we do, our whole history, happens on a speck. On something carried by a dark river towards somewhere we can only guess. It places us inside a story of a scale that's hard to even picture. But that's not a reason to feel small. It's a reason for awe. To see that our attempt to map this, to understand the pull, is the universe in a way starting to know itself. We are the part that can look back and trace the shape of its own path. Looking for meaning in that motion, that might be the most human thing we do. It ties our deepest wonder to the quiet, mathematical rules of gravity. We're trying to read a dance that began billions of years ago. And we are, in our way, part of it. We're not the only ones moving. Other galaxies are flowing in different directions, too. These are like siblings to our own anomaly, other bulk flows that don't quite fit the maps. Over in Centaurus, far beyond our local supercluster, there's a stream of galaxy clusters all heading toward the same spot. That motion covers 2.5 billion light-years. It seems to be pulled by something even bigger. A supercluster they call Hyperion, still forming. Its gravity is so wide it's moving whole neighborhoods of galaxies from that far away. And farther out, studies of quasars have shown bulk motions on scales that many thought shouldn't be possible. The size of these streams pushes against what the standard model predicts. Because on the largest scales, the universe is supposed to be smooth, homogeneous. Motion over billions of light-years should have been smoothed out by expansion. Finding these flows is like learning that separate continents are all tilting the same way. It means the gravitational landscape might be rougher than our simulations show. Then there's the dark flow. It was first seen toward our anomaly, but later searches looked for it elsewhere. Some studies say they see bulk motions in distant clusters that line up in ways you can't explain with any known mass in the observable universe. Whether that's real or noise is still debated. But the possibility raises a question. Are all these bulk flows ours and the others evidence that the cosmos is more connected than we thought? Studying these sibling flows is a comparison. If every large-scale motion can be explained by superclusters and dark matter, then our pull toward the Great Attractor is just normal cosmic geography. A common thing in a universe full of gravitational wells. We're near an interesting one, but not special. Just typical in a standard current inside the cosmic web. But if these other flows, especially the biggest ones, keep exceeding what models predict, then the message shifts. It would mean something's missing from our mass accounting, or maybe from our understanding of gravity on these scales. These sibling anomalies would together point to a gap in our knowledge. Our local mystery would be part of a larger pattern of deviation, a chorus of whispers from the dark, all saying the map isn't finished. So the search goes beyond our own path. By measuring galaxy motions in deep fields across billions of years of look-back time, cosmologists are taking the universe's pulse on a grand scale. They are asking if the tug we feel is just a local story, or one paragraph in a longer narrative about how structure forms across all of space and time. The answer will tell us if we're sailing a charted ocean, or if the currents we're tracing are leading somewhere uncharted. But the map is finished, and the numbers still don't match. So the search has to go somewhere else, somewhere speculative. The multiverse. It starts with a question about our own beginning. Cosmic inflation says space expanded incredibly fast just at the start. But what if that inflation never actually stopped everywhere? Eternal inflation is the idea that it's a perpetual process. It ends in some places, creating bubble universes like ours, but it keeps going forever in the space between them. So our whole cosmos could be one bubble, in a frothing, infinite sea of spacetime, a foam of separate realities, each with its own physics, its own history. There's no bridge between them, their light can never reach us, but gravity might be different. Gravity isn't a force inside spacetime, it's the geometry of spacetime. A warp in the fabric. And that warp, that geometry, might be able to leak across the boundary between bubbles. If there's a colossal mass in the bubble next to ours, could it make a dent in the membrane? A faint gravitational tug on our side, that's the multiverse idea for the anomaly. It means the dark flow, if it's real, isn't a pull from something hidden in our universe. It's the gravitational shadow of another cosmos, a neighboring reality brushing against ours. Picture two soap bubbles floating close. Their surfaces are separate. But if one bubble is much larger, its curvature might subtly influence the space around the smaller one. They don't touch, but they're not completely isolated. In that picture, our entire local universe, the Milky Way, Laniakea, Shapley, all of it, is being gently nudged by the mass of a universe we can never see. A ghostly pull from beyond any horizon. Now, this is at the very edge of science. It brushes against metaphysics. There's no direct test for it. No experiment we can yet imagine to prove a gravitational leak from another reality. For many scientists, it's just a thought experiment, a placeholder for any anomaly that won't fit a normal explanation. But its power is what it represents. It's the ultimate extension of the mystery. For centuries, we've pushed the unknown further away. First, it was a force in the forest, then a god on a mountain, a monster in the sea. In cosmology, we pushed it to the edge of the solar system, then the galaxy, then to dark matter and hidden superclusters. The multiverse pushes it one more step. It says the force pulling our galaxy might not be unknown matter in our universe. Its origin could be outside our universe altogether, in a separate reality with its own story, its own laws. That doesn't give an answer. it changes the question. The journey isn't just about mapping the cosmic web anymore. It becomes a search for the shape of existence itself. Are we alone in reality, or is our universe just one page in an infinite book? That quiet current carrying us through the dark might be the only clue we ever get. A whisper from another page, felt only as a gentle, unending pull. Gravity's story isn't only about what pulls, it's also about what pushes. For every mountain of mass in the cosmic web, there's a valley. A valley of near nothing. These are the cosmic voids, the vast, empty spaces between the filaments. They can span hundreds of millions of light years. They might hold just a handful of lonely galaxies. Their role in our motion is counterintuitive, but it's profound. They push. To see this, you have to think of gravity as a landscape. Not a simple magnet. The universe has an average density of matter. Think of that as sea level. A supercluster is a mountain range. It rises high above that sea level. Its gravity pulls everything downhill toward it. But a void is a deep oceanic trench, a region far below the cosmic sea level. In the geometry of general relativity, that underdensity creates a different slope. Matter naturally flows out of it, away from the emptiness toward the higher ground of the filaments, so a supercluster attracts, but a void effectively repels. It's a gravitational hill you roll away from. This isn't a mystical force. It's gravity's other face. Where there's less mass than the average, the curvature of spacetime creates a kind of negative pressure. And as the universe expands, these voids expand even faster. They are the great emptiers, growing, pushing their boundaries outward. That expansion herds galaxies out of the emptiness. It nudges them toward the dense walls of the web. Our local neighborhood is shaped by this balance. Behind us, in the direction opposite the Great Attractor, there's a significant void. Astronomers call it the local void. It's a vast, sparsely populated region. Our Milky Way sits right on its edge. As this void expands, it contributes a subtle shove. A real one. It's part of the reason we're moving away from it, and toward the dense concentration of mass in the attractor's direction. Our motion is the net result of a complex push-pull dynamic. We're pulled by the immense gravity of the Great Attractor, and the Shapley Supercluster ahead. And we're pushed by the expanding emptiness of the local void. And other underdensities behind, we're in a cosmic squeeze, caught between the mountain and the trench. This flips the entire perspective. The anomaly pulling us isn't just a destination. It's also an escape. We're flowing away from profound emptiness, as much as we're flowing toward profound density. The cosmic web is a structure defined by both its threads and its holes. To navigate it, a galaxy must respond to the full topography. The peaks of dark matter and the troughs of void. That realization adds a final layer of nuance to the map. It means to perfectly predict our path, we need to chart not only every hidden supercluster in the zone of avoidance, but also the exact shape and expansion of every void that borders our supercluster. The silence of empty space speaks as loudly as the gravity of 1,000 galaxies. Our journey is a flight from nothing toward everything, in a universe where absence and presence wield the same fundamental force. The ancient sky was this perfect dome, unchanging. For thousands of years across every culture, the stars were fixed, pinned to a sphere that turned around an Earth that didn't move. The cosmos was a stage. Humanity was at the center of a static performance. That idea, it was a comfort. It put us in a known place, a permanent location. The universe was a grand clock, but its gears didn't carry us. We were the unmoved center, just watching the heavens turn. That view started to fracture. With Copernicus, with Galileo, the Earth was dethroned, set into motion around the sun. But even then, the sun became the new center, a privileged spot. And the fixed stars, they stayed fixed. Distant, eternal, our solar system moved, but inside a vault that didn't. The real revolution in motion came much later. In the 1920s, Edwin Hubble up at Mount Wilson made a measurement. It shattered the static sphere for good. He found those nebulae, those fuzzy patches. They weren't clouds in our galaxy. They were other galaxies, entire islands of stars, and they were all moving away from us. The universe wasn't just large, it was expanding. Space itself was stretching, carrying the galaxies apart. That was the third great displacement. First, we lost our place at the center of the planets. Then we lost our place at the center of the stars. Now we lost our place at the center of the galaxy. The Milky Way was just one galaxy among billions, all of them adrift in an expanding ocean. But this expansion, it created a new kind of rest, a new frame. The cosmic microwave background, that fossil light from the Big Bang, it fills all space evenly. In a perfect universe, you could measure your motion against this uniform bath. You'd be at rest, relative to the universe's expansion. Then, in the 1970s, they found the CMB dipole, and that comfort was shattered too. We weren't at rest. Our entire local group of galaxies, we were plowing through that ancient light, over 200 miles a second. We were moving against the backdrop of creation itself. That finding, it was the direct precursor to the hunt for the Great Attractor. It proved we had a local motion, and that demanded a local cause, a gravitational cause. Each step in this history peeled back a layer of cosmic privilege. We are not the center of the planets. We are not the center of the stars. We are not even at rest in the expanding universe. We are part of a river of galaxies flowing toward a hidden mass. This gravitational anomaly, it's just the latest chapter. The most detailed one in this ongoing story. It reminds us that every time we think we've found a fixed point, a true frame of rest, the cosmos shows us another layer of motion. We search for stillness, and we find only current. This isn't a demotion, it's a revelation of a deeper reality, a more dynamic one. Our place isn't a fixed point on a map. It's a line, a trajectory through a structured cosmos, a flowing cosmos, one that's never been still, not since the first moment. You can see the abstract flow of galaxies become real. To understand the scale of the Great Attractor, the bulk flow, you have to move past words. You have to visualize it, and there are tools for that. They turn cosmic data into a personal journey. One of them is Space Engine. It's planetarium software, a digital universe built on real data. You can start at Earth, pull back past the Moon, past the solar system. Watch the Milky Way shrink to a spiral, then you keep going. You fly through the local group, past Andromeda, out into the ocean of galaxies. You can set a course for the heart of the Laniakea Supercluster. And you watch the velocity indicator climb. It shows your speed as you race along the same current that carries our galaxy. You can pause, turn, look back and see the filamentary structure. The great river of galaxies all trending inward. It turns numbers on a page into a three-dimensional reality. Another tool is Celestia. It's more of an open-source simulator. You can add community add-ons that plot thousands of known galaxies. You can install a catalog that outlines the Laniakea Supercluster. It draws its boundaries in glowing lines against the black. Flying through it, you get a sense of being inside a structure, not just looking at a flat map. These programs make you a cosmic traveler. They grant a perspective once reserved for supercomputers. For a more direct look at the science, there are interactive maps from the research teams themselves. The Cosmicflows project, led by astronomer R. Brent Tully, has published visualizations. Their videos, interactive web tools, they show arrows of motion superimposed on the galaxy distribution. Each arrow is a galaxy's peculiar velocity, its deviation from cosmic expansion. You play the animation and you see it. A convergence, a slow, majestic drift of countless arrows, all swinging to point toward the hidden mass in Centaurus. These aren't artists' impressions, they're graphical plots of the actual data. The gravitational signal made visible, watching them, you are seeing the pull. Institutions like the Hayden Planetarium or NASA visualization labs produce similar films. They use the latest survey data to animate the cosmic web. You search for terms like Laniakea Supercluster visualization or cosmic bulk flow animation. That leads you to these treasures. They're the closest thing we have to a time-lapse of our galactic destiny. If software feels too digital, a simple physical model works. Take a large, stretchy sheet of spandex, suspend it loosely. This sheet represents the fabric of space-time. Place a heavy weight in the center. A bowling ball, that's your great attractor. The sheet deforms. It creates a deep, sloping well. Now gently place a marble, your Milky Way galaxy, somewhere on the slope. It doesn't sit still. It rolls, tracing a spiraling path down into the well. That's the essence of gravitational attraction in Einstein's relativity. Mass tells space-time how to curve, and curved space-time tells mass how to move. To model the bulk flow, add a second, heavier weight far across the sheet. That's the Shapley Supercluster. Notice how the first well now tilts toward the second. The marble's path changes. It still rolls toward the first weight, but its overall trajectory is bent by the distant, more massive pull. You've just modeled the nested gravitational influences that guide our real motion. It's a hands-on demonstration of the invisible forces. Engaging with these tools does something. It bridges the gap between data and deep understanding. The mystery stops being a distant headline. It becomes a landscape you can explore. You're no longer just hearing about a current. You're feeling its direction, seeing its scale from a God's eye view. This active participation transforms awe. It turns it from a passive feeling into an engaged curiosity. It empowers you to ask better questions. What if I moved the weights? What if the sheet itself was expanding? These models and simulations make the cosmos accessible. They remind us the greatest mysteries aren't locked away in journals. They're waiting in the data, ready to be visualized, explored, personally witnessed by anyone with a sense of wonder. Our maps are incomplete. That's the quiet truth at the heart of all this. We've charted superclusters, we've built digital universes, traced the cosmic web. And still, a significant part of the mass pulling on us could be unseen. It might be hiding in the deepest parts of the zone of avoidance, behind thicker dust than we've ever gotten through. Or it could be in the most diffuse halos of dark matter, so vast and so thin that their gravity just blurs into the background hum of the cosmos. It escapes what we can measure now. We're mapping a shadow with a flickering lantern. The shape we see is real, but the full extent of it, that's still guessed at. Not known, and our measurements have limits. Peculiar velocity surveys, they're an incredible feat, but they're not perfect. To know a galaxy's true motion, you need its exact distance, phenomenal precision. Over hundreds of millions of light years, that task is full of uncertainty. Small errors in distance create noise in the velocity map. That noise makes it hard to separate the true signal of the bulk flow from random fluctuations. It's like trying to hear a specific melody in a crowded hall. The melody is there, but defining the exact notes, the volume, that's difficult. Because of this, the literature has an ongoing debate. Researchers publish papers arguing over the exact amplitude of the flow. Is it as strong as some say, or slightly weaker? They debate its scale. Does it truly span a billion light years, or is it more regional? One team's analysis might point to a startling deviation. Another team, using a different method, finds everything consistent. This isn't failure. This is the sound of science working. It's the process, refining our view of reality, pixel by pixel. That humility isn't defeat. It's the engine. The gravitational anomaly isn't a puzzle to solve and file away. It's a beacon. Its unexplained signal shines right on the frontier of what we know. It defines the questions for the next generation of cartographers. What will the next radio survey show in the zone of avoidance, with 10 times the sensitivity? What subtle pattern in the cosmic microwave background will a future observatory finally clarify? What new property of dark matter will theorists propose for the halos we can't yet detect? The unknown isn't a wall, it's a horizon, and the pull we feel, that's the compass. Pointing the way forward. The Andromeda galaxy is coming toward us. It's the biggest thing in our local group. That's about 80 galaxies held together by gravity. Andromeda isn't moving in a straight line toward the Great Attractor. It's more of a spiral, a slow dance that ends in a merger. That local motion, that collision course, is the main gravitational story for our galaxy right now. It's a strong, close pull that overshadows the wider, gentler current of the supercluster flow. But there's another layer. While Andromeda and the Milky Way are locked in their own embrace, the whole local group, that entire family is embedded in the larger river. It's moving as one piece, carried by the bulk flow toward the Great Attractor. So imagine you're on a ship, sailing down a wide, slow river. That river is the supercluster current. On that ship, you and another person are walking toward each other, drawn by a magnet you both hold. That walking, that meeting, is your local collision. It's urgent and direct, but it's happening entirely on the deck of a vessel that's being carried by a much greater force. The ship's destination isn't set by your walk across the deck. It's set by the river. That's the hierarchy of gravity. The strongest pull wins at its own scale. Inside the local group, the attraction between Andromeda and the Milky Way is the strongest force. It decides our local fate. But the combined mass of our whole local group is tiny next to the immense gravitational well of the Laniakea supercluster. So while we dance with Andromeda, our whole dance floor is sliding downhill, toward the Great Attractor, which means Andromeda is feeling the same vast pull we are. Its peculiar velocity, its deviation from cosmic expansion, includes that same component from the supercluster flow. We're companions in this larger journey, even as we're partners in a local merger. The other galaxies in our local group, like the Triangulum Galaxy, are part of this same nested reality. They orbit the group's common center of mass, influenced by the dominant gravity of the Milky Way and Andromeda. But their trajectories through the wider universe also include that steady drift toward Centaurus. Every galaxy we see nearby lives this dual existence. A life governed by local attachments and a destiny shaped by distant, colossal landmarks. It reframes our place again. We're not just a galaxy moving toward an attractor. We're a galaxy within a group, within a supercluster, within a flow. Our motion is the sum of attachments at every scale, from the bond with our nearest giant neighbor to the tug of a hidden heart 250 million light-years away. It's a reminder that in the cosmos, no journey is simple. Every path is a braid of influences, woven from the intimate to the infinite. Science doesn't just live in journals. A mystery this big, it gets into our stories. The gravitational anomaly, the Great Attractor. This idea of a hidden force pulling the galaxy, it's all over science fiction now. It's a cosmic plot device. It taps into something deep. In books, it's often a destination, the place you finally reach for revelation or for danger. Alastair Reynolds, in Revelation Space, he writes about ancient alien civilizations. They're all being drawn toward the galactic center, running from some great threat. So the pull isn't just gravity in that story. It's a current, a narrative current, herding species toward this final, mysterious confrontation. The attractor itself becomes a character. An indifferent landmark, a cosmic one, that dictates the fate of empires. In movies and TV, the idea shifts. It becomes a void, an anomaly, a place where physics is distorted. You see it in the spatial distortions in Event Horizon, or the gravitational anomalies in Interstellar that warp time. They don't name it directly, but the inspiration is clear. It's a hidden, powerful something that breaks the rules. It pulls ships and people toward an unknown fate. Video games use it as a setting. In Elite Dangerous, there are regions like the Formidine Rift. It's a vast, barely explored void. Strange gravitational signals there, hinting at something ancient and hidden. Pilots go there not for trade, they go for the mystery. To see what the pull is hiding. Now, these creative versions, they're not scientifically accurate. They're not meant to be. They take the seed of a real mystery, an unexplained pull in the darkness, and they let it grow into these narrative forests. They turn the attractor into a portal, or a weapon from a dead civilization, a sleeping god. They inject agency, intention, into a process that's actually utterly impersonal. Gravity doesn't have a motive, it just is, but that act of storytelling, it matters, it serves a function, it popularizes the science. Someone might hear Great Attractor first in a novel or a game, and that spark leads them to look up the real astronomy. These stories bridge a gap between abstract data and human imagination. They make the vastness feel navigable, even personal. They answer a need, a primal need. To look at a starry sky and not just see physics, but to see a story, our story. This cultural lens shows something fundamental about us. We are meaning-making creatures. Faced with a silent, mathematical force guiding our journey, we don't just ask how, we ask why. Fiction gives us space to explore those why questions. Even if the answers are fantastical, is the pull a warning, a welcome, a test? By exploring this, science fiction reflects our fascination with the unknown. Our deep desire to find intention, or at least a narrative, in the forces that move the universe. It turns the anomaly from a data point into a myth. And in doing that, it reminds us. Our quest to understand the cosmos is, and always has been, a profoundly human endeavor. The answer is coming from the next generation of telescopes. A whole new set of observatories on the ground and in space are being built right now. Their main job is to map the structure of the universe with a precision we've never had before. They're cartographers for the invisible, and their maps might finally show us the full source of the pull. Leading this is the European Space Agency's Euclid telescope. It launched in 2023. Its entire mission is to survey 1/3 of the entire sky. It will look at billions of galaxies stretching back 10 billion light-years. Its power is in measuring weak gravitational lensing. That's the subtle distortion of a galaxy's shape, caused by the gravity of dark matter in between. By mapping these tiny distortions everywhere, Euclid will create a three-dimensional chart of dark matter itself. It will trace the unseen scaffolding of the cosmic web. It will directly weigh the gravitational wells of structures like the Shapley Supercluster. And it will reveal any other massive things hidden in the zone of avoidance. Then in the next few years comes NAS, a Nancy Grace Roman Space Telescope. Roman has a field of view 100 times larger than Hubble's. That incredibly wide gaze lets it do sweeping surveys in infrared light, seeing through cosmic dust. Roman will do a galactic redshift survey on a staggering scale. It will measure the precise distances and motions of tens of millions of galaxies. That lets scientists map the peculiar velocity field, the true flow of galaxies, with a resolution that makes our current maps look like rough sketches. The bulk flow toward the Great Attractor won't just be a general arrow anymore. It'll be a detailed current, with every eddy and tributary measured. On the ground in Chile, the Vera Sea. Rubin Observatory will soon start the legacy survey of space and time. It uses the largest digital camera ever built. It will scan the entire southern sky every few nights for a decade. It will detect and measure tens of billions of galaxies and stars. Rubin's relentless watch won't just find faint, distant galaxies. It will track how their brightness changes over time. That gives another incredibly precise method for measuring distances, which then refines our map of how galaxies are moving. It's a census of the cosmos on an industrial scale. It will leave no major structure uncharted. Together, these instruments are a quantum leap. They'll move us from just sampling the cosmic web to imaging its full anatomy. For the first time, we'll have a complete inventory of mass, both visible and dark, across our entire local universe. We can place the Milky Way within this map and run the gravitational math with near-perfect inputs. The pull from the Shapley Supercluster can be calculated to a precise number. The contribution of the Vela supercluster will be fully accounted for. Every hidden filament and void will be weighed. The great promise is that this new data finally balances the cosmic ledger. The combined gravity of all these mapped structures would exactly equal the observed motion of our galaxy and its neighbors. The anomaly would be solved. explained by the grand but ordinary topography of the dark matter web. But the greater possibility is that the ledger still won't balance. That even with this flawless, comprehensive map, a residual, coherent flow remains, a pull that can't be attributed to any structure within our observable horizon. That result might be even more significant. It would be the strongest evidence yet for something beyond the standard model, a hint of the truly exotic. From modified gravity to influences from beyond our cosmic bubble, the mystery's final answer isn't just out in space anymore. It's being built in clean rooms. It's being coded into software, waiting for these new eyes to open and show us the true shape of the current we're in. Physics has mapped our journey, but the meaning goes deeper. We're in a very specific stream inside the cosmic web. A stable spiral galaxy orbiting a quiet star on a planet with liquid water and life. And you wonder if these facts are connected. Whether the particular gravitational current carrying the Milky Way is part of the reason we're here to see it. That line of thought has a name, the Anthropic principle. In its weakest form, it's just a statement about observation. We can only observe a universe that's compatible with us being here to observe it. It sounds circular, but it has power. It means that among all possible universes with different constants, or all possible regions with different conditions, we will always find ourselves in a place that allows for life. We're not a random sample, we're a selected sample. The one place where the question can even be asked. Now apply that to the galactic current. Our Milky Way sits in a quiet suburb of the Laniakea Supercluster. Not in the violent, collision-filled core of the Great Attractor. We're out in the flowing outskirts, and that specific location might be crucial. A galaxy thrown into the dense, turbulent core of a supercluster would face constant gravitational interactions. Close passes with other galaxies could disrupt its spiral structure, trigger huge bursts of star formation that sterilize planetary systems, or feed its central black hole into a raging quasar. Environments like that might be too hostile for the long, stable periods you need for planets to form, for life to slowly evolve. On the other hand, a galaxy completely isolated in a deep void might lack raw materials. The gentle accretion of gas, the minor mergers that fuel steady star formation, those could be too scarce. Its stars might grow old and quiet too fast. The galactic ecology could become impoverished. Our position looks like a Goldilocks zone. We're inside a flowing filament, feeling a gentle gravitational tug that provides large-scale structure and motion. But we're far enough from the most extreme densities to avoid constant disruption. This flow may have helped shape the Milky Way's history. It guided the accretion of gas that formed its disk. It set a rhythm for its star formation. It put us on a path that for billions of years has been stable enough for a planetary system like ours to arise and persist. So the speculative link is this. The same bulk flow that points toward a hidden gravitational anomaly might also be a necessary part of the cosmic environment that allows observers to exist inside it. The pull isn't just a curiosity. It might be a feature of a habitable galaxy. If the universe is a vast landscape of possibilities, we find ourselves not just anywhere, but in a specific kind of place. A place with a certain gravitational topography, a place in motion. This doesn't imply design or purpose. It's a recognition of conditioning. We are products of our cosmic context. The laws of physics and the initial conditions of the Big Bang set the stage. And within that play, the development of a spiral galaxy in a flowing filament, on a quiet arm, around a stable star, that was one possible outcome. Our existence is a testament that this particular chain of events, this specific current in the dark, was one that allowed the universe to become aware of itself. It ties our most fundamental question, why are we here, to the silent, mathematical drift of stars. We're not just tracing a current, we are a manifestation of its conditions. The pull is really about the shape of reality. We have to move past gravity as just a force. Newton's idea worked for centuries. It explained the apple, the moon, the planets. Gravity was an attraction acting across space. That's how we see the Great Attractor pulling us. But on cosmic scales, that's not the full story. Einstein gave us a deeper map. General relativity. Gravity isn't a force, it's geometry. Mass doesn't pull, it curves spacetime. Think of a flat rubber sheet. Put a heavy ball in the center. It makes a well. Roll a marble onto it. The marble isn't pulled by the ball. It just follows the straightest path on the curved surface, and that path is a spiral inward. That's the essence. The ball is a galaxy, a supercluster. The marble is the Milky Way. The sheet is spacetime itself. That changes how we see our journey. The bulk flow, all those galaxies moving together, isn't a collection of tugs. It's us observing the large-scale curvature of spacetime. We're measuring the topography of the cosmos. Over hundreds of millions of light years, the Great Attractor, the Shapley Supercluster, the dark matter halos, they aren't separate suspects. They're features in one landscape. Mountains and valleys in spacetime. The cosmic voids, those huge empty regions, they aren't neutral. They're the flat plains, the high plateaus. Matter flows downhill from them into the gravitational basins. So our galaxy's motion is elegant. Inevitable, we're not being pulled, we're in freefall, following a geodesic. The straightest path through a curved universe. It's like a river finding the path down a mountain. The water isn't pulled. It flows along the land's contours. Our galaxy flows along the contours of curved spacetime. Shaped by all the mass and energy, this view ties every clue together. The dark matter halos define the deepest curvature. The cosmic web filaments are the ridges and channels. The peculiar velocities we map are just galaxies rolling down these cosmic slopes. Even dark flow, if it's real, would be a tilt in the geometry itself. A curvature from beyond our horizon. This doesn't solve the anomaly, it reframes it. The question isn't just what massive object is out there. It's what is the precise shape of spacetime here. And why is it shaped that way? Our motion is a single data point, a vector. It helps cosmologists reverse engineer that colossal shape. It's a clue in the language of geometry. A whisper about the distribution of everything. So when we look toward Centaurus, we're not just looking for hidden mass. We're looking along a line of curvature. Tracing the warp in the universe. Our journey shows we don't live in a static void. We live in a dynamic, sculpted, flowing continuum. The anomaly pulling us is the universe revealing its own profound shape. There's a line we can't cross, a boundary written in light and time. Our observable universe is a sphere, about 46 billion light-years in radius. That's not the size of the universe. It's the size of the part we can see. It's the distance light has had time to reach us in the 13.8 billion years since everything began. Beyond that limit, it's invisible by definition. The light hasn't reached us, it never will. The space between us is expanding faster than light can cross it. That's our ultimate horizon, and it raises a sobering possibility. The main source pulling our galaxy gravitationally might not be hidden behind dust or in some void. It might be hidden beyond that horizon, in a region of space-time we can never see. If that's true, the implications are profound. An object beyond the cosmic horizon is causally disconnected from us. It's had no chance to influence our region through any signal except gravity. Gravity, as a warp in spacetime itself, might be the only thing that can leak across that fundamental divide. We'd be feeling the gravitational echo of a structure we can never see. A landmark in a neighboring province of reality whose light will never arrive. The Great Attractor and the Shapley Supercluster would then just be local features. Hills on a continent that's itself sliding toward a distant, unseen ocean. In this scenario, the anomaly becomes a permanent mystery, not because our telescopes are too weak, because the universe placed the answer outside our theater of observation. This forces a confrontation with the limits of knowledge. Science is built on observation, measurement, testable prediction. But how do you study something that is, by the laws of physics, unobservable? You work at the boundary. You use inference and theory to probe the shape of the unseeable, the precise pattern of the bulk flow we can measure. Its strength, its coherence across vast distances, becomes a clue. It's like feeling the steady tilt of a floor and inferring a massive foundation shift far below, even if you can't dig down to see it. Cosmologists build models. Mathematical models of possible larger-scale structures or gravitational geometries that could produce exactly the flow we see. They ask, if the universe extends beyond our horizon with a certain distribution of mass, what signature would that leave on our motion? Our journey becomes a diagnostic tool, a tool for mapping the invisible. Accepting this possibility isn't a scientific defeat. It's a profound upgrade in understanding. It means recognizing that our cosmic home, the entire glittering expanse of billions of galaxies we call the observable universe, is likely just a fragment. A single island in an archipelago of unimaginable scale. The pull we feel is the tide from a sea we cannot sail. This realization recontextualizes the quest. The goal shifts. It shifts from finding a final, visible culprit to meticulously understanding the implications of the signal itself. Every refinement of our maps, every new measurement of the flow, tightens the constraints. It narrows what could possibly lie beyond the horizon. We may never point a telescope at the source, but we might one day be able to say, with great confidence, that its mass must be this large, and it must lie in that general direction, relative to a cosmos we cannot see. This is where curiosity meets humility. It acknowledges that some questions, driven by the nature of reality, may have answers that remain eternally over the horizon. Yet, in tracing the arc of that pull, in mapping its effects with exquisite care, we are doing something remarkable. We are using the knowable to sketch the silhouette of the unknowable. We are reading the universe's deepest currents, not to reach a destination, but to better comprehend the vast, flowing shape of home. Mapping the cosmos is just too big for one institution. The data coming in from telescopes like Vera C. Rubin and Euclid, it's staggering, billions of galaxy images, all needing to be catalogued, understood. And this is where the story turns outward, to you. Because the human eye, the human mind, they're still unmatched at certain things, recognizing patterns. Seeing subtle shapes. That need has created this movement in modern astronomy. Citizen science, it's a direct invitation to be part of the search. Projects like Galaxy Zoo, they've been pioneers for over a decade. They show volunteers images of galaxies from massive surveys. Your task is simple, profound. Look at a galaxy, classify its shape. Is it a spiral? An elliptical? Something more peculiar? That basic act of recognition, it's irreplaceable. Computers can struggle. The appearances of galaxies are messy. Varied, but people excel at it. Every classification you make, it adds a data point to the map. It helps astronomers understand the distribution of galaxy types. And that traces the underlying structure, the large-scale structure of dark matter. You are helping to chart the web that guides our motion. Each click is a small act of cosmic cartography. And for those who want to contribute processing power, there are distributed computing projects. Cosmology at Home is one. It lets you donate the unused cycles of your home computer to run pieces of massive simulations, cosmological simulations, while you sleep or work. Your computer can help calculate the evolution of virtual universes, testing different models of dark matter and gravity, to see which ones produce a cosmos that looks like ours. You become a silent partner in a supercomputer, your machine part of a global network, probing the laws of reality. These opportunities, they represent a shift. A profound shift. The quest to understand the gravitational pull on our galaxy. It's no longer confined to mountaintop observatories or university labs. It's a collaborative endeavor now. Global. By participating, you transition from being a spectator of the mystery to an active participant in its solution. You help turn raw data into knowledge. This democratization of science, it means the map of the cosmic web. The map that shows our place in the current is being built with contributions from people all over the world. It makes the grand narrative personal, your curiosity, your effort. They become woven into the fabric of our collective understanding. You are not just learning about the current that carries us. You are helping to measure its depth, trace its source, and in this way, the greatest mysteries of the universe become a shared human project. Connecting our innate wonder directly to the frontier of discovery, our galaxy is still moving. It's riding a current that started at the beginning of time. That journey has gone from the faint warmth in ancient light to the hidden valleys of dark matter. From the continental sprawl of Laniakea to the quiet, speculative shores of realities we can't reach. The gravitational pull isn't just a destination on a map. It's a continuous lesson, a lesson in cosmic humility. It shows us that most of the universe is made of something we can't see. That our perspective is always local. That stillness is an illusion. Every new telescope, every refined map, brings us closer to balancing the ledger. The ledger of mass and motion. But the real revelation might not be a final answer. It might be the deepening understanding that comes from the search itself. We are part of a flowing, structured, and profoundly connected whole. Our quest to understand the pull is the universe becoming aware of its own shape. As we wait for the next generation of celestial maps, we continue the voyage, not just as observers, but as participants, in a grand, unfolding story written in gravity.